This is the first in a video series that's supposed to ease you into being able to do epsilon-delta proofs. Sometimes you'll find these epsilon-delta proofs for limits in a calculus class, or you'll definitely find them in a course on real analysis. But they seem to be really tough, and I haven't found a teaching resource that made them easier to do yet. I'll find things that give you a couple examples, but nothing that actually teaches you how to actually do them. Now, it's nothing that you can do in a single lecture. It's definitely going to take a series of them, and we're going to have to wade into this a little bit slowly. So before we actually do the epsilon delta proofs themselves, I think it's easier, I think it's more instructive to start doing some other proofs that are similar to them, that follow the same kind of style, so that it'll make it easier when we go to do the actual epsilon delta proofs. So what I'm going to primarily be doing here is we're not going to be showing that a limit exists for a function as x approaches a number. I find it more instructive to show to talk about limits when x approaches infinity. So this is the first part in a series that is going to guide us into hopefully proficiency with doing epsilon delta proofs. So I want to start out, the first thing I'm going to be doing is studying limits like this. What does it mean when we say that the limit of some function as x approaches infinity is infinity? Now, I start here because it's intuitive. We all know what it means. We've been doing it since algebra class. We say that a function rises right? As x approaches infinity, all that this really means is that a function keeps on going up and never stops. But what we're going to do here is mathematically find a way to objectively define what it means to rise right. We're really going to nail this down with notation and logic here. So let's see. Draw out a picture of what I mean. All right. When we say a function rises, so at some point, it could do anything around here. It doesn't really matter. But eventually, past some point, it's going to go up and keep going up and up and up forever. Now, what do we mean? What does it mean before we can actually go from that sort of informal statement of, oh yeah, it rises, to actually saying definitively that the limit as x approaches infinity is indeed infinity? Well, there's like a wordy definition for it, and I'm going to hold off on that until I give you the intuitive version. What it means is that to prove that something rises, then that means that no matter what number you give me, we'll say, I'll call that m. So I'll say it's m1. No matter what y value there is, there's always going to be a corresponding value of x somewhere out there, which we call n. I'll call it n1 to correspond with the m1. There's always going to be a value of x, which we call n1, such that whenever x is greater than this number, whenever x is in this region here, it causes the function to be above the value of m that you were given. So think of these m numbers as kind of like a challenge. All right? These are going to be large numbers, and you have to find values of x such that whenever x is greater than those, the values of the function will be in excess of m. So in this case here, as I have it drawn, if if this is my function f of x, doesn't matter, that's f of x. If I challenge you with m1, then that's this height, and here is the value of n, past which the values of the function will be greater than it. Well, you might say, all right, well then, what if I choose a larger value of m? Let's say m2. Well, if you choose a value of m2, if the limit really is infinity, then the same condition is going to hold. There's a different n value out there where the same thing happens again. And the idea is that this can be done no matter how big the m's are. All right, a portion of this is it's regardless of how large m is. So it could be way up here. I'll call it m sub 0. Doesn't matter. Eventually, if the limit really is infinity, then regardless of the size of m, there's always going to be a corresponding value of x, which we call n, say n sub 0, such that whenever x is in here, the function values beat that challenge value. All right, that's the idea. No matter how big you say, there's always an x that's, in a sense, is going to beat it. Now, in words, that can be stated a couple of different ways. So to actually make this statement, we have to show that this is possible. Now, I just have a drawing. This isn't a proof. So it's nothing that even approaches an epsilon delta proof. But the idea is still there, and that's the thing that has to be shown. So in words, it's written a couple of different ways. I have a couple of different ways of writing it. This is one way. Now, you might want to pause the video and write this down maybe, but you have to show that there exists a number n such that the function value will be in excess of m whenever x is greater than n. And that's just the wordy, precise definition of what I just showed you here. All right, no matter how big m is, there's always an n such that whenever x is greater than it, the function values will be greater than the number that you were challenged with. That's one way of saying it. A slightly different way of saying it is in order to establish that the function actually does rise, you have to show that for any value m, arbitrarily large, that's the key. It doesn't matter how big it is. That there must exist some number n, which is an x value, such that the value of the function will be in excess of m whenever x is greater than n. So, past this value, you're guaranteed to have this condition. So what that means is just a slightly nuanced other way of saying it is this. What you have to do, therefore, the challenge, is that you have to find the number n that makes this condition true whenever x is greater than n. You have to show that if this condition is true, then it must follow that the function is greater than m. What this is really all about is it really comes down to just playing with inequalities. All right, you have to show that you have to find an n such that the truth of this statement here implies this condition. All right, you have to show that this implies this. That's the essence of the proof. So I'm going to do that with a couple of real simple examples, because if you don't understand the easy ones, then the harder ones are just going to be way out there. But the easy ones should go pretty easily. We'll work through them, and hopefully you'll get the idea. Now I am going to show, I am going to prove this. I'm going to prove that the limit as x approaches infinity of a simple function, 1/2 x, is infinity. I'm going to prove that this thing rises right. So what I have to do is I'm basically gonna well, this is what I actually have to show. I have it written down. I have to find an n such that this function, which is this, will be in excess of m whenever x is greater than n. So the way that these all start is every one of these starts out with, and it's kind of implied, maybe this will be the last time I write it, but they all start out in words. They'll say let m be given. Alright, so you're already pre-challenged with it. Alright, you're challenged with some large number m. Well, you know what? I'm even going to backtrack here a second and just show. I'm going to show that this can be that this is true for some specific values of m before I do it with a variable. So let's see. The function f of x equals 1/2 x. So the challenge is I could say find a value of n such that this function will be in excess of, say, 1,000. Okay, so the challenge is we have to make the function 1/2 x greater than 1,000. That's what we have to show. So what you do is we have to find some kind of an inequality that's going to imply this statement here. typically the way it goes is you start with the thing that you want to prove, and you do what I think is called a forwards backwards proof. Alright, we want to arrive at this. So what I'm going to do here is I'm going to solve this for x, multiply both sides by 2, and that gives me x is greater than 2,000. And right now the proof is done. It's all over. If you know what you're doing. It seems kind of deceptive, but it really is done. Because check it out. We have discovered that the value of n that's going to make this thing true is 2,000. Now watch how this works. We want to show the truth of this statement. We want to find an x value such that whenever x is greater than it, this is going to be true. So we'll say let n equal 2,000. If n equals 2,000, okay, if this is true, then whenever x is greater than 2,000, we can work with the inequalities, multiply both sides by 1/2, and that implies the statement 1/2 x is greater than 1,000, and that's what completes the proof. We found it. Well, the proof that it can be made in excess of 1,000. All right, we showed that as long as x is greater than 2,000, it's a guarantee that the function will be in excess of 1,000, and that's it. That's all it is. So I could play this game all day. I could say, try to make 1/2 x greater than 10,000, and I would work the same way here. And I would get right, if I said all I could do is add another 0. If I say 10,000, show that 1/2 x can be made greater than 10,000. All I have to do is I work backwards and say, okay, if I multiply this by 2, I get x must be greater than x must be greater than 20,000. If I can reverse this somehow and show the truth of this from that, then it's all over. I just come up here and say, all right, I'm going to say let n equal 20,000. Then that implies whenever x is greater than that number, 1/2 x will be in excess of 10,000. I mean, this is easy to show graphically. Just take a little room up here. All that we really showed, if this is 1/2 x, all right, if I said to beat 10,000, 10k, the point here is 20,000, 20,000, comma, 10,000. All that we really did was show that whenever x is greater than 20,000, which is what we started at here, that implies that the value of the function will be greater than 10,000, which, you know, we go straight from here to here. The trick is knowing where to start. You have to get this first step. The step is that first step is the challenging part of it. But you kind of get sort of a roadmap of how to go about this. If you start with what you want to prove, try to isolate an x from it, and then say, okay, that's going to be my starting point. If I start here, can the steps be logically reversed that are going to give me what I want? And in this case, it's true. So, well, that was only true in the case of 1,000 and 10,000. If I want to set up an actual proof for this, I got to start all over again. I'll say let m be given, and now we want to find an n such that I abbreviate such that by st. Find an n such that 1/2 x will be in excess of m whenever x is greater than n. So I have to find some value of n such that this statement will imply this. I just got to do the same thing. I mean, even if you just take a little bit of guesswork, if you want to beat some number with this particular function, all that you have to do is make the value of n equal to twice the number that you want to beat, because it's 1/2 x. It's a very simple function, but it serves a useful purpose for instructionally. So we'll start out, let m be given. So that is given, and you want to make 1/2 x be greater than m. So all that you do is, again, you start here and just reverse these steps. Multiply both sides by 2, and we'll get x is greater than 2m. So then that's what you're going to do. You're going to say let n be equal to 2m. Right? That's the number that you're going to let x be greater than. So if n is equal to 2m and x is greater than n, which is equal to 2m, then from this statement it necessarily follows, if you multiply both sides by 1/2, you get 1/2 x must be greater than m, and that completes the proof. Okay, we found we found the value of n that makes this statement true, and that particular value of n happens to be 2m. So it's twice the number that you're challenged with if the number is if the function is 1/2 x. I guess seeing that this constitutes a proof is tough in itself, so you may want to go back and check this out a couple of times, make sure that you get all the details down. But these are the easiest types to understand. So it goes with, like, there's kind of like a discovery phase in it, right? You start with what you want to show, and you sort of work your way to kind of like a guess as to what the value of n is going to be. And then this is the trying it out phase, or the verifying phase. Once we come up with this, we kind of test it out, and we say, okay, suppose that n is equal to that number and x is greater than it. Does that imply what we originally wanted to show? And in this case, the answer is yes, because you can just multiply both sides by 1/2. So that's enough to show this is the formal proof of the statement, the limit as x approaches infinity of 1/2 x equals infinity. Because it doesn't matter how large m is, we showed that all that you got to do is pick a number twice as large as it. So that's one. I'm going to do another easy one that's kind of close to this. I'm going to show that the limit as x approaches infinity of radical x is actually equal to infinity. So what do I have to do? I have to find, now clearly it's true, but I have to find a value of n such that radical x will be in excess of m, no matter how big m is, whenever x is greater than n. So find a value of n such that this statement implies the truth of this statement. And again, this is pretty simple. It's very similar to the one that we just did. We want to show this. So what I'm going to do is I'm going to go through like the discovery phase of this and just square both sides of it. All right. So that'll give me x is greater than m squared. So right now I have an x on one side and I have a number over here, and I'm thinking to myself that this could probably that if I let n be this number, then that's going to imply this. Might be a little, again, it's a little bit tough to see at first, especially if you're not used to doing this or thinking like this. But basically this is all it is. So we're going to say let n equal m squared. So in other words, if you challenge me with, say, make radical x larger than 10, I'm going to say, well, make n greater than 100, right? The square of that. If I say make n greater than if I say make radical x greater than 100, then the value of n is going to be 10,000. So let's see, so it's basically just going to be the square of the number that you're trying to beat, because it's a square root function. But let's see how this works out. Let's do the actual proof part of it. You say, all right, let n equal to m squared, so that if you're allowing x to be larger than that number, that implies that x is greater than n, which equals m squared. And if x is greater than m squared, it automatically follows that you can square root both sides and get radical x is greater than m. Thus, the proof is complete, because this is valid no matter how big m is. And that's what we have. So we found the value of n that works for this particular function. It happens to be m squared. So no matter how large a number I tell you to beat, if I say make radical x larger than 1 billion, all that you have to do is say, oh, alright, well, I'll just make x bigger than 1 billion squared. That's going to do it. That's the way it goes. Those are the easiest ones to do. In the next video, I'm going to take another step up from this, something that's not quite as simple as this, but the principle is going to be exactly the same. And hopefully we will be on our way to being able to actually figure out the hardcore epsilon delta ones.